Hello, welcome to another stream. How about that? Today we continue doing whatever we did yesterday. Check out the previous VOD, the genetic programming part 1 VOD, for more information on what we're doing. So on the previous stream we started doing visualization. Today we're going to continue doing it, and I want to also finish the simulation. Right now, in the definition of the game, well, we only have 3 kinds of objects on the board. Agents, we have food that the agents can eat, and we have walls that the agents have to bypass or something like that. That's pretty much it, and we only implemented visualization of all of that stuff so far. Let me try to recompile that. This is how the visualization looks like. We have an obvious problem here. Sometimes the objects are generated on already taken cells. So we're gonna fix that a little bit later. Another problem is that the food is supposed to be colored green. And the reason is bug of GFX, SDL GFX that we're using. Field circle color function that accepts the renderer that is used for render things. The parameters of the circle, the first 2 things are the center of the circle, this one is the radius. And then it accepts the uint32, the value of the color. There's another one where you can provide the components of the color separately, but it's not really convenient because we have a color in the form of u32. We have a code that parses the u32. What if we create a macro called hex color that accepts obviously hex? And guess what it expands to? It will expand to that literally. Instead of doing it like that, you can just do it like that. So basically it expands to several arguments simultaneously, even though this function accepts more arguments. Let's go to the field circle. We're gonna use RGBA, I think. So if you try to use this function, obviously it's not gonna work because you have to provide more arguments, but then you can do hex color, wrap it like that, and now everything is colored correctly. What's the next problem? You're not spawning things on already taken cells. The easiest way to approach that would be to have some sort of a function is cell empty, and it accepts the game also a cell position X and position Y. The easiest way to do that is just to iterate through all of the agents and iterate through all of the foods and all of the walls and just check if they have the corresponding coordinates. Game agents I pos X equal pos X, or their pos Y equal to pos Y, then we're gonna return true. The time has come to introduce some sort of point or coordinate, because doing this kind of stuff all the time is not a particularly great idea in my opinion. I'm gonna define struct, actually type def, and this is gonna be X and Y. We're gonna have a point here. Let's call it point. Coordinates. Yeah. Point position, and for the wall we're also gonna have a point position. Unknown type point. Like, why are you saying it's unknown? Excuse me. I just renamed point to coordinate and I instantly forgot that. My brain is so pepega. And we need some sort of a function that tells us whether coordinate equals coordinate A, coordinate B. AX equal BX and AY equal BY. Chord equals this position. There we go. And then we can return false. There we go. So now we have a special function that checks if there's something on a particular cell. And now we need to integrate all of that into the game initialization. Random empty chord on board. Chord result. We might as well introduce random chord on board. This entire thing is going to be result. X is equal... Let me copy paste this thing because this thing does exactly what I want here. There we go. And then we just return this thing. And while, if it's not empty, we keep generating that until it's empty. And then we return this thing here. When we're gonna have such situation? So, okay, so somebody was talking about checking whether the board is full. So we need to make sure that this thing is like that. When we're generating a random agent, random empty coordinate on the board. Alright, so, but that only works for the agents, it doesn't work for foods or anything like that, so it's gonna be init game. Then for the foods, random empty coordinate on board. For the wall, it's the same, random empty coordinate on the board, game. As you can see, everything looking good. To be fair, we are not initializing the seed. And maybe this is something that we need to do. srand and use time 0 to initialize all of that, so let's see how it's gonna go. Every time I run this thing, it's gonna be different. I see different combinations. Alright, seems good, seems good. Interestingly enough, I can assign some sort of a key, and every time I press that key, I can reinitialize the game. Right. Yeah, I can just look at different combinations of the game. We can try to increase the amount of agents, more different combinations. So I think the time has come to implement a simulator that will simulate the game. As I already mentioned at the beginning, classically, the genetic algorithms are implemented by encoding your solution into a string. So, and that string is called chromosome, and each individual character is called a gene. In case of this kind of Turing state machine, each individual row of the table can be considered a gene, and the whole table can be considered a chromosome. And maybe we don't even have to encode anything. Maybe we can work directly on mutating and crossovering brain cells themselves. So in our case, brain is a chromosome and brain cell is a gene. And maybe this is exactly what I need to call them. But I kind of like a brain cell and brain, but maybe gene and chromosome would be a little bit better. And at the same time, maybe we're gonna actually have a fixed amount of genes in a chromosome. We're gonna have genes count, 20 of them, like 20 slots in your chromosome. If we're gonna cross over them, crossbreed them, we can just divide it by half and just give the halves to different agents. And this is chromo. Yeah, so it's actually agents count, right? So because we have each chromosome associated with the agent, step the game. So for each individual agent, to step the game, we just need to iterate through all of the agents and step a single agent. Game, agents, I. So we're gonna take the state of the agent. Now, I also need to iterate through all of the chromosomes. Through all of the genes of the agent. It's gonna be J, so we have genes count. The state machine here, like a single gene, consists of like 4 things. The current state of the agent, what the agent sees on the next cell in front of it, what action it needs to perform in that case, and what state it have to switch after performing that agent. So it's gonna be game, chromos, I, then we take a look at the genes. So Jth gene of ith chromosome. In the genes, we also have a state. And if that state corresponds to the current state of the agent, that means we probably found the right gene. Now we need to figure out what's the environment of the agent. Env of agent. I think we need to accept the index of an agent, agent index. So we need a function that takes an index of an agent and tells us what the agent is currently seeing. So we have a special type that describes what the agent can actually see. Do we want to wrap around our board? I think we do. So I want to iterate through all of the foods count. And we need to actually come up with the point at which the agent is looking. Something like coord in front of agent. So it's going to be agent. We need to take the position of the agent, the direction of the agent, combine them somehow and get the coordinate in front of it. So how can we do that? I think we should come up with the table coord dirs, and we're gonna have like 4 of them. So we have right, up, left, and down. Right, to go to the right, you need to just increment 1. X. Up is gonna be 0, -1. Left, -1, 0. Down, 1. There we go. We have all of the possible directions. We take the direction of the agent, we can call it a delta, and then we can come up with the result where this thing could be initially equal to position of the agent. So it's going to be x plus dx and y. Yeah, I'm actually doing that in the wrong function. God damn it. And then I can return the results. And nothing is not implemented to do. There we go. It compiles. Oh my god. And if it compiles, chat, say the line, chat. It works. But to be fair, I wanted this entire thing to wrap around. Result x plus. It's actually, this one has to be y. We need to have something like mod. It's gonna be board width. Let's implement mod int. So we have a and have b. A plus b and mod b yet again. Then we take board in front of the agent. We need to find what's in front of the agent. We iterate through all of the foods. If game foods I position coord equals coordinate of in front of the agent position, that means we can instantly return environment food. We just found it. Next thing is going to be essentially walls. Nothing special. So we have walls, and similarly can have agents. If the state of the agent matches the state of its corresponding gene, the next thing we have to check if the environment of that gene corresponds to the object in front of the agent, game I. And if it does, we literally found the right gene to perform. Maybe it makes sense to take this thing, gene, like this. So here's the current gene. If we found one, we have to perform an action. So what's going to be the action? So we have to provide the game, we have to provide the index of the agent, and we have to provide the action. So the action is in the gene. You see? So this is basically what gene encodes. And it codes what the state the agent has to be in, what the agent has to see in front of it, and then what action it has to perform. And after we perform that action, we have to take our agent and switch it to the next state according to the gene. Next state. You see? This is the whole interpretation of the chromosome. It's kind of cool because this is pretty much the Turing machine interpreter. Let's do perform action. So we have to accept the game, then we're gonna accept agent index, and then we're gonna accept the action. And depending on the action, we're gonna do different things. Maybe you should call it execute action, I'm not sure. And yeah, let's replace this thing. Right, we're gonna replace it with colons, case, and maybe after the case, a break. What do we do in case of a nope? Nothing, because it's a no operation. What do we do in case of a step? We just step unless there is a wall in front of the agent. So we take environment of agent, game, agent index, and if the environment of agent not equal environment wall, we're gonna try to step. We need chord direction of the game agent's agent index dir, right? So you get the direction. We can take this thing, position X, and essentially add this thing back. Maybe it would be better to have like a separate function for that because I think it will get a little bit convoluted after some time. So it's going to be step agent, game agent's agent index, and then we're going to have step agent, and then like this. It's going to be mod int. So this is X, and what we're wrapping around the board width. And here we're going to have a similar situation for each axis, and this is going to be height. And I guess that's pretty much it. So the next thing we have to do, environment of agent. If the agent has to eat, we take a look at the environment, and if it's equal to environment food, first we have to kill the corresponding food. Also increase the hunger. And the same thing is gonna probably go if you see another agent in front of you. Attack action is not implemented. Eat action is not implemented. We just don't have like a set of the right functions to do that, because I can just check what kind of entity in front of me, but I cannot take that entity. Turn left. So what are the direction? We have right, up, left, down. Turning left is increasing. Turning right is essentially decreasing. So I can take the dir +1 and mod around it. Game agents, agent index, direction, mod int, direction +1, 4. The same thing will go for this one. Let me actually go to the compilation errors. There we go. Now we need to implement these things. We need auxiliary functions, food in front of agent, game, agent index, and it will return you the pointer to the food. Then you can modify it if you want, but if it cannot find any food there, you will get a null pointer. Food in front of agent is not implemented. So I want to have like a similar thing here where we're gonna have wall in front of agent. I think I can re-implement that slightly better. Food in front of agent. I provide the game and agent index. Only if this entire thing is not equal to null, only then we can try to eat the food. I take the food and I mark it as eaten. And then we have to increase the hunger. Yeah, but we're gonna call the hunger. In that case, this is agent index. Hunger, we're gonna increase it, but how much we can increase it actually? I don't know. Food, hunger, recovery. If greater than hunger max, we'll have to sort of set this entire thing back to hunger max, because there's no min-max functions there. Agent in front of agent. Very funny. We have agent index, and if agent that we found in front of agent, other agent, is not equal to null, we have to try to attack that agent. And obviously agents with like a smaller index have a priority in this situation. Other agent, we're gonna take their health, attack damage. We're not going to check deaths right now, and I think we implemented everything so far. Make agents drop the food when they die, because I don't really want to work on that right now, at least. We have to decrease the hunger. Handle hunger. Let's keep it as a separate step. So this one is agents count. For each individual agent, hunger, we're gonna decrease it. Step, hunger, damage. Is that a good name for this variable? I don't know. If hunger is less or equal than 0, we're gonna declare the health of the agent equal to 0. They instantly die. You have to be careful with this kind. We need a food in front of the agent. For all of the foods, if game agent's position, we have to give this in front thingy, if the coordinate equals to the position of the food we're currently exploring, that means we have to return the pointer to that specific food. I think I can implement the rest of this thing by copy-pasting this entire. So instead of food, this is going to be agent. For the wall in front of agent. Now I kind of want to re-implement this function in terms of the other function that I just implemented. So we have food in front of the agent in front of the agent, blah blah blah. Food in front of agent not equal null. I'm gonna return env food, and I don't have to do this thing anymore. So just the sequence like sequentially checks all of these things. Cool. I already call step game when I press space. So you see, it already steps the game, but it doesn't really do anything. So I press space, it doesn't do anything. Well, I mean, I just pressed R to regenerate it, but yeah. And this is because all the genes, I presume, are filled with 0. So when we initialize in the game, we also need to go through all of the genes and initialize them as well. Game, chromo, and for each individual gene, we have to generate like a random thing. This is what we need to generate. Super quick. Game, chromos, I, genes, J. How many states do we have? As many states as the genes themselves. Random int range from 0 to genes count. Environment. We can implement a function called random environment. Then we can generate a function random action, and then we can do the same thing. So a random chromosome for a particular agent. Does the compile? No, it doesn't, because we don't have a random environment. Let's implement that. Random environment. For the environment, we also need to know like how many different environments do we have. So I'm going to introduce this trick where we have environment count. I'm going to introduce action count. What I can do now is return random int range from 0 to env count, and similarly a random action, this kind of thing. We have random genes. I'm pressing the space and it does nothing. It literally did nothing, unfortunately. I don't know why. It's kind of sad. Also, I think I forgot a very important thing. For the food in front of the agent, the food should not be eaten. Also, agent should not be dead. Okay, so they rotate it. Random stuff doesn't really do anything. How many genes do we need to have? We need all possible combinations of states and environments. Their genes just don't do anything in this particular situation. We can try to dump one of their genes. Print chromo, iterating through all of the genes. First thing is the state. We're gonna have a function environment as sister. Action, the state again, but it's the next state. For the environment as sister, switch upon all of these things and just convert them to a sister. A sister means C-string. That's what it means, okay? In case of a count, I'm gonna say assert unreachable. Action as sister, like that. Return, boom. I want to try to print the chromosome of the first agent. Print chromos 0. So this is what we got. I have a feeling that we have too many states. That's what causes the situation. The initial state is 0. If you have an agent in front of it, you have to try to eat the agent. And then switch to the state 10. And in the state 10, if you see a wall and stuff like that, I think the problem here is that we have too many states. Let's actually introduce the amount of states. Like let's just cap that. 5 states. Now we have less amount of states and we have a little bit of redundancy. So we start at 0, and if we see nothing, we're gonna try to turn left. So some of them will start doing something. Okay, let's see. They're actually doing, and then they stopped. Well, at least some of them managed to generate a loop. Let's imagine that we have a board 30 by 30. Majority of them just rotating. I think like for all of that to have effect, we just need to... Oh, look at that one! What the f is it doing? And obviously, like, there's something wrong with rotation. I want to separate a lot of this stuff because we have too much code in a single file. I'm gonna use like a single compilation unit. This is how many functions I defined. Jesus Christ, that's a lot of function. So there's the main, which contains an entry point and implements an event loop, a game module that implements the logic of the game, visual module that implements visualization of the game state, and in the future we're going to have a separate module that is responsible for training particular population and whatnot. Why does it make 2 steps? Something is really pepega up here, by the way. I want to implement a feature where I could simply click on the agent and it will dump the state of the whole agent to the standard output, and then I can explore what is going on there. What we need to handle here, I think, is mouse button down. So it's an event mouse X, mouse Y. So if I press this thing, this is actually perfect. It basically rescales the position of this thing for me automatically, which is actually pretty cool. Take X and Y, divide them by cell width and cell height and get the coordinates. We can floor fit and cast it back to int. This is cell X, this is cell Y. I think we need an additional function. Agent at. I'm gonna iterate through all of the agents that we have. Chord equal position chord. We instantly return the pointer. Otherwise, we don't return anything. If we do have an agent here, print agent. You see, it doesn't matter what I click here, it doesn't print anything, but if I print on the agent, it shows that its direction is right. At some point we can click on them again and we can see that their hunger is decreasing. And at some point I think they should become dead. And we have a bug for some reason. Hunger can become negative. We still render dead bodies. Health is greater than 0, that only then we're gonna render them. Step a couple of times until all of them are dead. They all starved to death. Nobody managed to sustain themselves. Maybe make them transparent or gray color if they're dead. Not a bad idea. Agent alive color, dead color. This thing looks super weird. It's not supposed to even do things like that. Alright, so they're kind of grayish now. Yeah, it moves really weirdly. Maybe the step agent is falling through. I know what is going on. It goes through all of the genes, but what it has to do, it actually has to stop and switch to the next agent. After that, we have to break, actually. They get executed several genes in a row that fit. It's funny how this thing got in front of the food and doesn't know what to do with it. And they got dead. We just need to generate more agents and see what's gonna happen. Look at that one! and they're all dead. How about like 500 of them? 1000 agents. 1000 of food. Some of them will figure out how to eat food. None of them figure it out. More agents? How about 2000 of them? We had a pretty good progress today. We finally finished the rules, the first pass of the rule design, and we definitely need the second pass of the rule design because the rules are too complicated. We want to simplify them. Another thing we need to implement the like making new generation, at least manually. And once we have this thing manually, we can try to automate that. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you tomorrow.